Please get out your note packet and turn to Lesson 1.3, Properties of Real Numbers. Fill out your notes as you watch this video. Remember, at any time, you can pause the video to catch up on your notes. Today, we're talking about the real number system. The real number system contains natural numbers, whole numbers, integers, rational numbers, and irrational numbers. Take a minute to label your chart as follows. Remember, if you need to pause the video, do so. All right, natural numbers. Natural numbers are the numbers that you learned to use when you first started counting. Natural numbers are numbers like 1, 2, 3, 4, 5, and so on. We remember natural numbers by calling them the counting numbers. So natural numbers are known as the counting numbers. For algebra purposes, we will actually use the name natural numbers. The whole number system is the same as the natural number with the addition of the number 0. The whole number system, 0, 1, 2, 3, and so on, is the same as the natural number with the addition of 0. So we remember this as the natural numbers plus 0. Integers are positive and negative whole numbers. -3, -2, -1, 0, 1, 2, and so on. We remember the set of integers as the whole numbers and their opposites. It's the set of whole numbers and their opposites. I'm going to give you some examples of rational numbers. Rational numbers are any number that can be written as a fraction. Rational numbers are decimals. They can be positive or negative. They can be fractions. They can be repeating decimals or terminating decimals. They can even be the square root of perfect squares. Remember that any rational number can be written as a fraction. Rational numbers is any number that can be written as a fraction. Remember, it includes positives and negatives, as well as terminating and repeating decimals. The last set in the real number system is the irrational numbers. Those are numbers that cannot be written as fractions. They are numbers like pi, or maybe the square root of a non-perfect square, like the square root of 50. Irrational numbers are also decimals that never repeat or terminate, like the decimal 0.010110111, and so on. It has a pattern, but the decimal doesn't repeat. So an irrational number is any number that cannot be written as a fraction. Remember that irrational numbers are the square root of a non-perfect square, decimals that go on forever.
Kimberly teachers, new teachers, just a reminder of the meeting in the library this morning. You need to take your device, actually take your hands up, your great hands up.
All right, I'm going to draw a number line very quickly just to remind you of the sets that you work with quite often, okay? So I'm going to draw a number line, and I'm just going to put some positive and some negative numbers on here, and then I'm going to plot the different sets. So I'm starting with integers. Integers, remember, are the set of whole numbers and their opposites. So -2, -1, 0, 1, 2, and 3. Remember that an integer is not a decimal. It cannot be a decimal. It is also not a fraction. Whole numbers. Whole numbers, remember, start with the number 0. Whole numbers, again, are whole numbers. They are not fractions or decimals. And then the natural numbers start with the number 1. 1, 2, 3, 4, 5, and so on. Again, natural numbers cannot be decimals or fractions. Lastly is this whole set of real numbers. Remember that the real number set includes all 5 of these subsets. And so the real numbers are every single space on a number line. The real numbers include every single space on a number line. All right, now we're going to identify the real number subsets that each example belongs to. There may be more than one answer. The first one is the square root of 45. 45 is not a perfect square. And remember that any number, the square root of any number that is not a perfect square is irrational. If you were to put this into your calculator, you would get a decimal that does not repeat or terminate. It just goes on forever. Irrational. Number 2, -4. That is an integer. Remember, integers are the set of whole numbers and their opposites. It is also a rational number. -4 can be written as a fraction. Number 3, 1/9. Well, 1/9 is a fraction, so it is a rational number. I also know that it is rational because it is a repeating decimal. Number 4, that is pi. Well, pi can never be written as a decimal because it doesn't repeat and it doesn't terminate. It goes on forever and ever. So pi is irrational. The next one is the square root of 64. Well, the square root of 64 equals 8. And 8 is a natural number. It is also a whole number. It is also an integer. And it is a rational number. Number 6 is the decimal negative 1.25. Now it is a decimal and it terminates, so I know because it is a terminating decimal that it is a rational number. Number 7 is 8, and you'll see that number 7 is exactly the same as number 5 when we simplify it. So it has the same subsets. The last one, number 8, is the decimal 0.010110111, and that is a decimal that does not repeat or terminate. It just goes on forever and ever. So it is irrational. It is irrational. All right, now I want you to use your foldables and identify each property. The first one, 3 times the quantity 2x minus 1 equals 6x minus 3. You can see here that we distributed by multiplying through to get rid of the parentheses. This is the distributive property. Number 2, 4 plus the quantity 7 plus 6 equals the quantity 4 plus 7 plus 6. We have moved our butt. This is the associative property of addition. Number 3, 5 plus 0 equals 5. This is the additive identity. The number stays the same. The additive identity. Number 4, negative 9 plus 9 equals 0. This is the additive inverse. This is the additive inverse. Number 5, 3 times 1/3 equals 1. This is the multiplicative inverse. We multiply by the reciprocal. We are multiplying by the reciprocal. Number 6, negative 8 times 1 equals negative 8. This is the multiplicative identity. This is the multiplicative identity. All right, we're going to evaluate each expression. We're going to name the property used in each step. I believe these are filled out in your notes. I may not use the exact same steps or methods as are filled out in your notes, but you should be able to pinpoint which step I did first. 2 times the quantity, 3 times 2 minus 5 plus 1. What did I do there? Well, I actually replaced the 3 times 1/3 with the number 1. What is that? 3 multiplied by its reciprocal, 1/3 to equal 1, is the multiplicative inverse. All right, the next step is 2 times the quantity 6 minus 5, close my parenthesis, plus 1. What did I do in that step? I just multiplied. I multiplied 3 by 2 and I replaced it with the number 6. You can either call this step multiplication or you can use simplify because that's really what we did. We simplified. All right, let's look at the next step. 2 times the quantity 1 plus 1. What did I do in that step? I just took 6 minus 5. We know that 6 minus 5 is 1. We can call that subtraction or simplify because we just simplified. The next step is 2 plus 1. You'll see that I eliminated the 2 times 1. Well, I know that 2 times 1 equals 2, and that's the multiplicative identity. Any number multiplied by 1 is that number. Lastly, 2 plus 1 is 3. And again, that's addition or simplify. All right, let's look at our next example. The first thing that I'm going to do is rewrite the problem. 25 plus 15 plus 14 plus 36. I have changed the order of the addition problem. Changing the order is the commutative property. This is the commutative property of addition. I just changed the order. Why did that do that? Save my recording somewhere. Of course not.